Hi, everybody. I'm sorry about my voice. I was practicing on the pommel horse and I injured myself, and now my voice is going to be this way forever. Anyhow, let's go talk about rates of diffusion and Graham's law of diffusion right now. Actually, I have a confession to make. I didn't injure myself on the pommel horse. I just inhaled some of this helium in this balloon. And because my voice box makes the molecules resonate at a certain frequency, helium is much lighter than the air we normally breathe, and that's why you sound all squeaky, because the molecules can move around much faster, creating a higher pitch. And you can figure this all out with a simple law, an equation: the rate of diffusion, rate of molecular motion of gases, and Graham's law of diffusion. So let's talk about all that right now. No, right now.
Well, hi everybody, hi, Mike here with my regular voice. Hey, we're here to talk about rates of gas diffusion and effusion. Now, diffusion is the movement of molecules from high concentration to low concentration. So, in other words, maybe you've done this before. Have you ever released a gas, and even though there were no drafts in the room, you know what happens with gases is their movement is very random, and eventually they'll fill the container that's available to them, and that can be sometimes embarrassing. But nonetheless, even without any sort of help, gases will move around randomly, and the rate that they do that depends on a couple of factors. Effusion, or effusion, whatever way you want to say it, is the diffusion through a porous membrane like something like a balloon. And we'll talk about that in a little bit when we take a break. Now, what I want you to do is realize that we're really talking about physics here. So if we have some energy imparted to a particle, let's make it relatable. Let's say that one of the things is a golf ball, which you know is lighter than a baseball. And some sort of magic apparatus, boom, projectile maker takes and puts the same amount of energy into the golf ball as the baseball. The kinetic energy of those objects will be the same, but it will be manifested differently in their speed. So the golf ball will go much faster than the baseball, and then if we're thinking like gases, they'll both, say, whack into a wall and then bounce off, and the big thing, although it's going slower, will bounce off. And if it was a perfect world and this was an elastic collision, then what would happen is the pressure would actually be the same, because the baseball will move at a slower rate, but its higher mass will allow it to have the same kinetic energy. All right, so basically what I'm saying is lighter particles move faster and bigger particles move slower, but they have the same, even when they have the same energy. All right. Now, what I want you to do is start thinking of molecules as populations. I want you to think of something like this. So let's say we have air in a container. It's sort of like, I always joke around, it's kind of like cars on the highway. If you could say, hey, well, what's everybody doing on the highway? Everybody's doing different stuff on the highway, all right? If you live around here, sometimes you've got, if this is I-35, you've got somebody on the shoulder going next to no speed at all, or very slow. This would be someone from Clark County, and they have like chickens in the back of their truck. And then, everybody's kind of doing something around what you'd call the most probable speed, or this dot, which is called the root mean square speed. Now, can we both agree that these dots are pretty close to each other, and we can avoid some of the mathematical complication of my explanation? Basically, a lot of the molecules are doing something around the middle. And let's say this is a sample of air, like you blew up a balloon and this was everything going on. But then there's some radical molecules going really, really fast. This would be like this is some guy in a green Dodge Charger who just bought the thing a week ago, you know. But basically you have some extremes, but most things are doing what's around the middle. Now, if we take something like helium, we would find that this curve sort of starts in the same place, and it would be kind of spread out more, but then, something like that. And you notice that the most probable speed and the root mean square speed, are a little bit shifted further out where the speed is higher, and we'll calculate that, we'll prove it. The way you do it is with something called Graham's law, or this equation. This is the equation for root mean square speed. It is the square root of, this is what we call in science 3, that's just 3. I'm avoiding a lot of the sort of mathematical derivation of this stuff. It's just a tool. This is called the gas constant, but it's not the one that you've been using quite a bit, the 0.082. It's the thermodynamic one that has got different units, all right? But it's a constant, so we're not going to worry about it. This is the temperature in Kelvin, and we'll talk about temperature changes another day. Got to be in Kelvin. You can't have negative speed, so it's got to be absolute units. And this is the molecular mass of the object in kilograms per mole. But you know what? That's if you want to get the exact value for the root mean square speed of a gas at any particular time, which is somewhat limited in its application. I mean, this number that crunches out of this equation isn't really worth anything unless you're going to solve problems about how gases behave relative to each other. So you don't have to have this in units of kilograms per mole if you're comparing two gases, which we're going to do just next. But first, check this out.
All right, fun little experiment. I've taken two balloons and I've pumped up one of them with helium, which is, of course, you can tell it's trying to float. And I've made them about the same size, okay? Just roughly, not exactly, but yeah, that's about the same size. And this is air. And according to Graham's law, the gas in the helium balloon is moving around at a relative rate of 1 over the square root of the atomic mass of helium. And given that this is air, and by the way, is it air? I blew it up with my breath. Could be a lot of CO2 in there, a lot of ethyl alcohol. But there's stuff in there that, if it is CO2, weighs more than the 29 grams per mole that air is. So even if it was just pure air that I blew out of my lungs, the helium, would be moving around at a rate about 2.7 times the rate of air. So let's come back tomorrow and see what happens to the volume of these balloons and which one will get smaller, quicker.
Okay, we'll come back and check on my balloons a little bit later. I might have Freudian slipped in there and gave away something like what we're going to do here. Here's a problem. Calculate the ratio of the rates of diffusion or effusion of air and helium. So let's do both separately. But our main weapon is the root mean square equation, 3RT over m. And that's going to be, and they give it this little, sometimes give it a little U bar as its symbol. Depends on what textbook you got. Don't get worried about symbolism and all that. And now, let me just say this. For this particular example, you could go and calculate 3R and T and just say pick a temperature, but you don't get any style points for that. It's all constant. So what we're going to do is compare the variable that is changing, and that is simply square root of 1 over m. And I'm not going to even, because I resent doing work that's extra. To solve this, if I just want a ratio of faster moving gas to slower moving gas, I don't even need the exact speed. I just need to know how they differ versus each other. So I'm only going to compare the things in here which are variables. All right. So let's go and say we'll do helium over here. And we'll do air over here. Now, I kind of rounded this. Air is really like what? 79% nitrogen and 21% oxygen, and then like 1% argon. I know they didn't add up to 100%, but it's a little bit less than 29 grams per mole. But let's make life simple. So I'm going to go ahead and I'm going to get a number which, once again, by itself is meaningless. 1 over 4 for helium. 1 over 29 for air, and then I'm going to calculate it on my calculator, which is where you calculate things. Of course, this is just going to be, let's just say I can do that in my head, the square root of 0.25, which I believe is going to be 0.5, but let's get to this first. Okay, so 1 divided by 29, this is going to be square root of 0.03448. All right, and then we're going to get a result of that. I'm going to do this one right now since it's on my calculator. So hit the square root button, and I get 0.18. I'm not even worried about what units it's in. All right, 5.695. Because I'm just going to compare that to this number, which is 0.5, and then square root of 0.5 is, square root of 0.25, I should say, is 0.5. So, look what happened. The number for helium, which is the number that is proportional to the average speed, is greater. And then, you know what we like to do with our ratios is usually you divide. Bigger number by smaller number is the way I like to do it. I suppose you could say take the smaller number divided by the bigger number, but I don't like to do that because I like my ratios to be greater than 1. So 0.5 divided by 0.185695 is 2.69 to 1. 2.69 to 1. Or helium, it's always good to frame your answers in the form of a sentence. And of course I made a helium diffuses 2.69 times faster. There's our answer, folks. This has got a fancy name called Graham's Law. It's basically just comparing the root mean square speed of two gases. And once again, if the temperature or the only things that can change in this equation is this equation is temperature and mass. That's the only levers nature can pull or push. So let's do one more example problem after I go check on my balloons. Okay, here we are, not quite 24 hours, more like 15 hours later. I want to get back to doing your video, and I'm excited about doing that, and I want to get this part over with. But here's our helium balloon. You can see, relative to the air balloon, much of that helium has diffused, effused, whatever word you want to use, out of the balloon. Now think about it. It's the fact that it's moving around 2.7 times faster than the molecules in that balloon. There's many more opportunities to collide with the sides of the container, which in this case are, you know, if you look on a very, very microscopic level, are porous, and the gas can leak out, as happens with all balloons, but certainly much slower with the air. You can try this at home if you're really, 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 really bored. Okay, and in economics, they call this deflation. Yeah, I don't like myself sometimes. Okay, let's get back to your video. Okay, gang, that was interesting.
sort of. So let's do another one. This one has a different spin on it. So now we got an unknown gas, and we're going to use its speed to determine its identity. They even tell us it's a noble gas. They tell us it has a rate of effusion, which is the equation. The same equation governs both diffusion and effusion. So if you see fusion, okay, of some form, you use the same equation, which is 1.875 times greater than chlorine. Give the identity of the gas. Well, it's a noble gas, and I can tell you what, gang, I already got my answer nailed down to 3 potential outcomes. Cl2 is about 71 grams per mole, and krypton, xenon, radon, they're all going to be heavier, so they are all going to move faster on average. So my answer is either neon, argon, or helium, and I don't like guessing. So what I'm going to do is I'm going to go ahead and I'm going to calculate the result for chlorine. So I'm going to go and get a chlorine value. By the way, once again, square root of 3RT over M. But, I'm just going to go ahead and say square root of 1. Okay, now chlorines are 35.5 apiece. But remember, this is Cl2, so times 2, 71, 35.45, 70.90. And I'm going to get a value for that. I'm going to go ahead and take 1 divided by 70.90, and that's going to be square root of 0.0141, which is some number, which, once again, is meaningless by itself till I compare it to something else. I know a lot of textbooks have an example where you do go calculate the average speed, but I never understood the utility of those problems, just maybe to get you used to using the equation. I don't know. Now, that's for chlorine. They told us in the text of the problem that this other unknown mysterious gas has a value that is 1.875 times greater. So I'm going to take and multiply that value by 1.875, and I'm going to get another number. That's the number that's proportional to the root mean square speed of the gas, 1.875, whoopsie, 1.875 times 0.11876, and this is going to be 0.2227, we'll call it, 0.2227. What's that? That is square root of 1 over m of the other gas, but we don't know what it is, so we will call it x. Square root of 1 over x is equal to 0.2227. Oh boy, how do I get it x? Well, I can tell you order of operations. I'm going to square it, and then I got 1 over x on the left, right? So if I square both sides, square, multiply it by itself, of course what I would get is 1 over x over here. What's important is that I do it to 0.222. Bang. 0, okay, let's be careful here. I don't miscalculate zeros. 0.0496 equals 1 over x. Okay, I'm going to invert it. I'm going to do a 1 over x with my 1 over x button. I don't want to brag, but my calculator has a 1 over x button. 20.16 equals x. Now, what we got to do is remember, this ain't math class. The name of the game ain't finding x. Well, it is, but then we got to think about what the heck did x mean? X in the equation was the molar mass of the gas. And I go look it up, and I can tell you right now, that's neon.
neon is the unknown gas, ladies and gentlemen. And that is the solution to our problem, which you can actually determine the identity of gases by their diffusion rate. And there you go. That's just another way you could identify something by one of its unique physical properties, which is, of course, its molecular mass. So, all right, that is Graham's Law in a nutshell. And I will see you folks in the next one. And until next time, have a good whatever it is that your day, night, wherever it is, wherever you are. Bye.